Hi everyone. Today we're going to be talking about topic 6b, which is measurement calculation of PV work. So just a reminder where we left off in the previous topic 6a. At the end of the topic, I mentioned the fact that in order for us to measure delta E, which is the quantity that we're looking for, remember that's a change in the internal energy for a given chemical reaction, we have to measure two components, which are heat and work. So if we can measure heat and work associated with every chemical reaction, then we can add those two numbers together and obtain delta E. So topic 6b is associated with measurement of one of those two components, which is work. And specifically, we're going to look at a special type of work called PV work. So the first thing is just to talk about what PV work is. PV work is also called expansion work. So this is a specific type of work that a system can do. And what kind of work is PV work? Well, it's a work that accompanies either expansion, in other words, volume increase, or compression, or volume decrease. Okay? So anytime you have a volume increase in a reaction or a volume decrease in a reaction, then PV work has happened in that situation, in that reaction. Because volumes increase and decreases only occur mostly with gases, we don't really think about PV work happening with solids and liquids, but we only consider PV work happening with reactions that contain gas particles, and specifically when you have different number of gas particles in the reactants and products. So what are some examples? First example that I wrote here is combustion of octane, which is a component of gasoline, C8H18, and of course we know that that comes as a liquid. So if you combust gasoline, or octane in this case specifically, the balance equation is shown here. You notice that we're going to need 25 oxygen particles or oxygen molecules in the gas form, in this case, for this reaction to completely happen. And we produce 16 CO2 gas and 18 water in the gas state. Okay? Now, this is the type of reaction that will result in an expansion or a volume increase. And the reason is because if you count the number of particles of gas on the left side, on the reactant side, you find that there's 25 because the octane is a liquid. And then on the right side, you have two gas particles. So if you were to count both of these, add them both up, you have 34 gas particles. In other words, you're going from 25 gas particles to 34 gas particles. And as you remember from the previous topic on gases, if we have more gas particles, that means we're going to have an expansion if volume will increase if the other two components are kept constant. So this is really the idea of it, is that when you have these kind of reactions where there is more gas on the product side, then you're going to have an expansion, and because of that expansion, work is being done by the system. And I'll show you a picture now to illustrate that. And you want to forget about this equation for now, but if you imagine what's happening is looking something like this. So let's say you have a piston, you have some weights here on a movable piston, and inside this container is your gases, is your reaction. So just imagine it's the same as the reaction we just talked about, which is combustion of octane. So you have the octane and the oxygen initially. You are able to perform a combustion reaction here, and then you produce your CO2 and H2O gas. Once that happens, of course, the gases will expand because you have more gases now. So they're going to push up, and when they push up, they're doing work against these weights, right? So that's where the work comes in from. It's when they're pushing against that weight, they're doing work, and that's called expansion work. Now, this is for an increase in volume, right? So you're going from a smaller volume to a bigger volume. But it's also possible that you go from a bigger volume to a smaller volume. So just imagine that you have the reverse reaction. Let's say you mix CO2 and H2O, for example, and you produce gasoline and oxygen. Now, this is not a realistic example, but there are other reactions where You're going to get fewer gas particles as a result of two gases combining together. And what you see when you have a volume decrease, if you have fewer particles of gas in the products compared to the reactants, then you're going to get a volume decrease, and that's referred to as a compression. So if the reaction goes from a larger volume in the reactant to a smaller volume in the product, that's called a compression. But the equation you'll use to calculate the amount of work that you get in terms of how much energy is is produced or is lost as a result of the system having this expansion work, having this PV work, is calculated using the same equation whether you have expansion or compression. Okay. Now what I'm going to do now in the next slide is derive an equation that expresses this work, this expansion work. Okay. Now the main thing to remember before I derive this is to remember the concept. The concept here is that because the work that accompanies the change in the volume, in the number of moles of gases, is associated with gases, you can then express the work itself in terms of properties of gases, and specifically we're going to express the work in terms of pressure and volume of gases. So that's why this type of work is often called PV work, because as you'll see, the equation itself is composed of pressure and volume. Okay. All right, so I'm going to derive this equation in the next slide. Okay, so we're going to start to derive this expression by remembering that our expression for work, which remember is the force times distance, right? Because remember that work is defined as the amount of force that's being applied on an object to displace it a certain distance away. So you got force times distance. And what you have to remember then coming from here is that you want to bring this expression and relate it to properties of gases. So one of the things you have to think about is what is the property of gas that has some relation to force. And if you think about that, you should come up with pressure, because remember that pressure is equal to force per unit area. Okay, so in which case we can then write force as pressure times area. So that we can substitute back here and write pressure times area times distance. Okay, so that's our three parameters right there for work. And then so what we want to do, of course, at this point we can see that this is pressure, that's already a property of gas. Now we have area and distance. Now if you have remember like that system that I was showing you in the slide earlier, which is the system of piston. If you have a piston starting from here and then it goes eventually to a piston that ends up at this level, okay, so it moves up a certain height, a certain distance away from where it's starting from, right? So here's the ending point, here's the starting point. So it moves up this height. Now there's an area, of course, that's part of that piston. Maybe this is a cylinder of some sort, so there's surface area, and then it moves up a certain distance. So if you multiply that area and distance that it moves, of course you get volume. Okay. Now what happens here is that's the volume change that happens. So you have starting volume and you have final volume, and this is the amount here. The volume that you're calculating here is that's your change in volume, or delta V. So in other words, we have then our expression for work, which is pressure times change in volume. Okay, so that's the basic expression. However, we want to think a little bit about this, because if you think about expansion, okay, if you think about expansion, earlier we discussed expansion. It should be clear that the final volume in an expansion, in other words, after the expansion stops, compared to the initial volume before the expansion starts, I mean, the final volume must be bigger than the initial volume. That's in the case of expansion, right? And then for compression, it's exactly the opposite. For compression, you're going to have the final volume being less than the initial volume, because you're starting with a bigger volume and you're going to a smaller volume. So if we do delta V always has the same meaning delta V is always calculated by taking final minus initial. So in the case of an expansion, your delta V is a positive number. In the case of compression, your delta V is a negative number. Now this pressure that you put here is the external pressure. It's the external pressure that the system is working against. So if in the case of expansion, you're pushing up against, either atmospheric pressure or some amount of pressure that's being applied on the gases. So you're pushing up against that external pressure. For compression, you're being pushed down by that external pressure. Okay, so now what you have to think about is then what is the sign of work. So if I just write this equation, P external times delta V, okay, in the case of expansion, because delta V is positive and pressure is always positive, pressure is never negative, as a result, in the case of expansion, I would get W being a positive number because I have a positive number multiplied by another positive number, right? So in the case of expansion, I'm going to get a positive work. In the case of compression, I'm going to get negative work because my delta V is negative, my pressure is always positive. But if you think about this, this is really not, it's exactly the opposite from what we're looking for. Because if you think about expansion, expansion means the gases are doing work. It means the gases are pushing up against the surroundings. So the gases is our system. So if the gases expand, that means it's doing work. Now, if something is doing work, by our sign convention, the work should have been what? Negative, right? So the work of the gases should have been negative if it's expansion. And so in other words, we want this to be actually negative, and we want the compression, which is when the surrounding is pressuring down on the gases, we want that to be a positive number. Okay, so in other words, if we just use this form of the equation, okay, we would actually get the exact opposite sign than what we expected. So to correct for that, what we do is we put a negative in front of this equation. So then the complete equation then becomes expansion work is equal to negative P external times delta V. Okay? Okay, so going back here to our slide from earlier, again, in the case of expansion, you're expecting the system to do work. So if the delta V is positive, the pressure is positive, then in order to make that work quantity negative, because the system is doing work, we need to put that negative sign in front of it. So the equation itself is work is equal to negative P external times delta V. And again, I want to emphasize that this equation can be used whether you have an expansion, which is an increase in volume, or you have a compression, which is a decrease in volume. Either way, you use the same exact equation. Okay.